Okay, good afternoon. A couple of announcements. How many of you have how many of you have seen or viewed the posted announcement about the quiz solutions? Okay, how many of you have seen the quiz solutions? How many of you have never used the class notebook before? That's fine. All the information is there. It's for the benefit of the students. So if you've not seen the class notebook, all the quiz solutions are already in there. Okay, that's what the announcement was about. So now there's one more reason why you should open up the class notebook. Okay. All 4 quizzes are in there. Grading is ongoing, so the grades should be updated in the next couple of weeks. Within the next week or so, we should be all caught up with the grades and everything. Look through the solutions. Several students had asked me a couple of questions, so I had informed the students. My response was that, once I post the solutions, review them, and then be better if you review them and learn them, and then you come back with specific questions, right? And that way I can address all of them with informed learning. Okay. That is the first announcement. The second one is that in terms of the course material, so far, even before we begin this lecture, in terms of the course material, we are halfway done. We are 50% of the way done with the course material itself. It might not seem like much. It seems as we might be going slowly, but there are a lot of slides in each of the lectures. So from here on out, not here on out, sorry, we are in the middle of the 5th week. So in terms of time, we are not even halfway done. Okay, we are kind of, I would say, either at least in sync or even a little bit ahead in terms of time. And we'll probably end up finishing the course early in week 10. Probably. That's my guess, best guess at this point. Okay. All right. So the material so far was based on your prereq materials like resistive circuit analysis, KCL, KVL. Voltage and current division is something you may or may not have seen before, but now, of course, you have seen those. Now it's the time to apply everything that we have learned so far. Okay. So one of the things we're going to look here is application of resistive networks and what can we do with it. All right, so here there's a design problem. It's asking us to design a resistive network that accepts an AC input, and you're asked to change the DC level of this AC input. Okay, essentially that's what it's asking for. So it's designing a resistive network that's going to accept an AC input and then apply a DC component to it. So as a brief refresher, we introduced AC and DC at the beginning of our course. AC voltages and AC currents are quantities that do not have a fixed relationship or fixed value with respect to time, meaning their value is a function of time. It changes at any given point in time. So if you're talking about voltage as a function of time, we refer to it as V of t, current I of t. T can take any values, 0.1 microseconds, 0.2 microseconds, milliseconds, seconds, it does not really matter. All it matters is if you have V of t or an I of t, is a function of time. All right, so that's AC. We saw AC, there are sine waves, square waves. I believe you have in the lab, you have used both sine waves as well as square waves, right? You have used both. So let's talk about what a square wave is, okay? Square wave is a subset of a rectangular wave. So rectangular waveform is basically has this shape, and it's a flat line at the top. So it's like a flat DC line for a small portion of time. And typically we say that this is the on cycle and this is the off cycle. So if it goes, AC waveforms have both positive values as well as negative values, right? So this kind of waveform is centered exactly at 0 volts right here. That's our ground reference. And the positive half cycle is typically noted as on, and negative half cycle is typically noted as off. The ratio of these cycles is known as a duty cycle. So a duty cycle is the amount of time the waveform is on to the amount of time it is off. Okay, so again, a duty cycle is T on over T off. If duty cycle is 50%, then the rectangular waveform is known as a square wave. That's it, as simple as that. It's not the actual shape of the waveform, okay? Sometimes, our brains automatically think, oh, it looks like a rectangle, so it's a rectangular waveform, and it looks like a square, so it's a square waveform. That's not what makes it a square waveform, okay? It's the amount of time. So if it's on half the time and it's off the other half of the time, that's a square waveform. The height does not matter. The waveform could look like a rectangular pulse, but if it's 50%, then it's a square wave. Yes. T on over T total. Ratio of. You're right. I'm so used to some things that we never stop to think about it. But the point being noted here, or the question being asked is, wouldn't it be T on over T total? And the answer is yes, it is. So T on to T total. Essentially, if the on time and the off time are equal, so it's a 50% duty cycle. So T on over T total. You're the only student who pointed it out in both sections, not just this. Okay. Now, have you all used oscilloscopes in the lab, right? On the oscilloscope screens, and it's very difficult to notice, but have you noticed on the left side of the waveform, in the middle of the waveform, there is an arrow pointing out, and see this sort of a symbol? Does anyone notice that? Some of you. Well, next time you're in the lab and you're using the oscilloscope, take a look. All oscilloscopes, if you look at the left side of the screen on the waveform, it'll show you a ground reference. It shows a ground symbol. That shows you where the center of the waveform is. Not the center, sorry. It shows you where the reference of the waveform is. For a pure waveform like this one, half of the waveform is above 0 and the other half is below 0. So this waveform goes plus 5 volts and minus 5 volts. So it has a positive peak and it has a negative peak. Okay. So it's going 5 volts above and 5 volts below. So the total swing in the amplitude of this waveform is 10 volts. So it is known as a 10 volt peak to peak waveform, P-P. 10 volts peak to peak waveform. It just says 10 volts peak, 10 VP. That means it's only talking about one peak. Okay. If it's peak to peak and it's 10 volts, that means it's 5 above and 5 below. If it's 20 volts peak to peak, then it's 10 above and 10 below. All right. Your function generators in the lab, like the ones we have behind us in this room, maximum output from all function generators that we see in academic environments is 20 volts peak to peak. Yeah, we cannot, that equipment cannot supply more than 20 volts peak to peak. Okay. But 20 volts peak to peak is only about 7 volts RMS. Right. Okay. So the center of this waveform is at 0. Okay, the center of this waveform is at 0. If we shift, sometimes we have a need to shift this waveform. either in the positive direction or the negative direction. So shifting the center of the waveform, either positive or negative, is known as clamping. Okay, is known as clamping. You're clamping the waveform at a certain level. This is very important because it's an important application because we have amplifiers. Amplifiers take the DC energy source and provide it or combine it with the AC input signal. And so at that time, we are introducing DC component or DC levels into our AC waveform. At the output, we want to remove this DC component. So if our waveform has shifted up, we need to bring it back down. If our waveform is shifted down, we need to bring it back up. And so this process is known as clamping. Okay, because you're clamping the waveform at a certain level. Okay, that's what it's asking us to do. So in this design problem, we have this kind of waveform, square wave plus minus 5 volts, a total peak to peak swing of 10 volts. And then we are asked to obtain this kind of waveform. Okay. This is our input voltage, hence V in, and it's a function of time, so V in of t. This is the desired output voltage. Nothing else is given to us. The only thing given to us is the input voltage and the desired output. And then the only constraint is use resistors, use a resistive network. Nothing else. No mention of current, no mention of power. There is no other constraint in the design. Okay. And we are asked to produce this 5 volts peak to peak. And because it's shifted up, this is 0 volts. So ground reference is now here. Let me note this down. Ground reference right there. All right. And that's what we want. Okay. So this can be easily accomplished with a diode. One single diode, and you take the input and you feed it into the diode. Diode is a one-way device, so it's only going to conduct in the on cycle. In the off cycle, it just cuts it off. And hence, you get 0 to 5 volts at the output. But the diode is going to eat up some voltage inside of it. And so instead of having 5 volts, in real life, you would get only 4.3 volts. So you would get the desired outcome, but it won't be 5 volts. It'll be like 4.3. So the waveform will have that correct shape, but it'll just be 4.3. Okay. Anyway, so we are not going to do that. We are asked to use only resistors. Okay, only resistors. And so what we can do is we can take a source and a resistor, and we can connect it to V in of t. V in of t is given right here. And these are arbitrary choices. Right. Okay. They're arbitrary choices, completely random. This is because we are not provided a constraint for current. It does not say design it for an output current of like 10 milliamps or 100 milliamps or whatever. So we could very well choose 1K, 10K, 5K, 100K, or any value for that matter. Okay. So we have V in of t, we have 10 kilo ohms. And we are going to see how we can do this. Okay. So if we want to get it above 5 volts, we need a 5-volt source. So our desired output needs to have a 5-volt source. And the 5-volt source is also fed through a 10 kilo ohm resistor. If both resistors are the same value, then it's going to cut out the negative half cycle. Okay, it cuts out the negative half cycle. So this kind of network is like very common. In our design, we are provided with a source of 9 volts, right? And we want to obtain 5 volts. So 5 volts from a 9-volt source is easily accomplished by using a series resistive network, meaning using voltage divider. If you use a voltage divider network, we can easily obtain any voltage we want. You could apply 9 volts to 9 resistors of equal value, and you can obtain any voltage. You can obtain 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, you can obtain a voltage of any value you want, but we want 5 from 9. Okay, so our resistive network, we can just do 2 resistors and obtain an output value of 5 volts. So our circuit will be modified like this. We have a source. This is our 9-volt source. This is our V in of t. And then let's see this. This is our desired output. V out. It's R2 and R1. And this is V in of t. Okay, that's our circuit. And we want plus minus 5 volts here. Okay. Let's take a pause. Let me know if you have any questions. So what equations do come to mind if you want to obtain 5 volts from a source of 9 volts? Or what theorem comes to mind? I'll answer it. Thevenin theorem. So you want to find the Thevenin equivalent voltage. We have a source of a certain value, We have resistors of a certain value. That resistors should combine and give us a specific value of 10 kilo ohm. That means we want the desired Thevenin resistance to be equal to 10K. So if we apply Thevenin theorem, our desired VTH, Thevenin voltage, is 5 volts. Our desired Thevenin resistance, RTH, is 10 kilo ohms. And we have seen this kind of circuit. We just saw it the last two classes, right? You have a single voltage source, you have two resistors in series, and how we can obtain the desired voltage and resistance. RTH is R1 parallel R2. And so this is R1 times R2, or R1 plus R2. Excuse me. And we have set this to 10 kilo ohms, right? That is set to 10 kilo ohms. And then our desired Thevenin voltage, VTH, can be obtained from voltage division. So it's our source, 9 volts times R1 over R1 plus R2. And this must be set to 5 volts. Remember, in your professional careers as engineers, this is what you're going to do every single day, every single month, every single year. You have a goal and you have to reverse engineer. This is our goal, whether it's a system or an application, software, does not really matter what it is. And then you're working backwards to design something that will satisfy that goal. Yes. So question being asked is, how come they both have to be 10K resistors? They can have any value. Or how come they have to be the same value? It's a good question. There was another question that was asked in the earlier section, which was, why is that source 5 volts? And without doing a full analysis, I could explain with the full analysis, but I didn't have a good answer. I'll explain a little bit, but I don't know if that's going to satisfy the question. Okay. So the response is, I don't have a good answer. I'm going to look into it and I'm going to bring the answer before next class. So this question as well as the other question. So the question being asked now is, why are both resistors the same value? And the question that was asked in the earlier section was, how come the source has a value of 5 volts? How would we know to keep the source at 5 volts? The simplest answer is because we want the shift to be plus 5 volts. Okay. But if I do an analysis, I can explain that. So I can explain the answer sort of with the analysis. Okay. But I don't have a better, simpler answer. So if we have plus 5 volts here, we are applying a source of plus 5 volts on the left at the top resistor right here. So this end of the resistor, the left end of the resistor, is always at plus 5 volts. Okay. The right end of this resistor is where it's going to fluctuate, right? So it's going from -5. So it's going from 0 to plus 5, back to 0 and -5. So the swing that is being provided at this end is going to have 5, 0, and -5. So the voltage drop across 10 kilo ohm resistor goes from 0 to plus 5 to plus 10. Okay, 0 to +5 to +10. So that's the only explanation I have so far, but I need to come up with a better one. Okay, so hopefully by Friday. All right, let's continue with this. So once we apply Thevenin's theorem, we have both RTH and VTH equations. We can plug the second equation into the first one, and we can obtain this expression right here, where we can rearrange the terms and determine the value for R2. And R2 value comes to be 18K. And once you have R2, we can calculate R1. Okay. So let's take a pause and let me know if you have any questions. Any questions?
I have a question.
Yeah, go ahead.
Is the purpose of this circuit to have the 9 volts power supply act as if it's 5 volts? That's what the whole purpose of it is?
Yes. So
Oh,
question
okay.
being asked is the purpose for it to act as 5-volt source? Yes, the answer is yes. Okay. All right. This can be verified in SPICE. So you can design the circuit in LT SPICE, create the circuit, the exact same values. You're going to apply V in plus minus 5 volts. So this is plus 5 volts. This is minus 5 volts. And the output goes from 0 to 5. Okay. The way we would design the input in LT SPICE is by supplying or inserting V1 or inserting a voltage source, go into the advanced tab, meaning describing the voltage, and you would choose pulse. And in pulse, you're defining the parameters. You're saying it's going from -5 to +5 volts, step 0, and then 1 microsecond is as like a transit time. You have to specify how long it takes for it to go from -5 to +5. And we describe it with like a very, very small value. So it's put as 1 micro. You can put it like 1 nano also, and it will work just fine. And it just creates like, okay, in 1 microsecond, it goes from -5 to +5. And then the next time it goes from +5 to -5, it takes 1 microsecond. That's all it's describing. That's just the way that the waveform has to be described. Okay. And then 1/2 cycle is, sorry, 1 full cycle is 2 milliseconds. And 1/2 cycle is 1 millisecond. And then we are not doing a DC analysis. So no .dc or .op, you're going to choose transient analysis. Transient analysis will place a .tran function. And in .tran, we are simulating from 0 to 4 milliseconds right here. 4 milliseconds. And again, steps of 0 to 1 micro each. So you have that many data points. And then once you run that simulation, you should see that output voltage or output waveform. Okay, this is easily done in LT SPICE. So definitely go ahead and do that when you're doing learning outside of class. Okay. All right. Yes. If we chose 10K at the start, we could choose 1K and 1K. We could choose 5K and 5K, 100 ohms and 100 ohms. It'll still work the same. And we can do that in LTSpice. And actually, the next slide after this is an example of what happens when we choose a different value. Yeah. One final point about this is that we have 3 resistors in the circuit. And so what is the equivalent resistance that is available at the output? Well, that will be the Thevenin resistance of the entire circuit. And because there are voltage sources in there, the Thevenin resistance of the entire circuit is all 3 of them in parallel. So 10K in parallel with 10K gives us 5 kilo ohms. Okay, so all of them are in parallel. That gives us 5 kilo ohms. And then let's say you're designing this for a customer, but the customer comes back and says, hey, I want the same circuit, but now I want it for a low power application and a high power application, for example. Okay. So low power and high power. Nothing is mentioned about voltage. Say voltage is the same. And you want more power. What needs to change? Well, power is the product of voltage and current. P is equal to VI. So voltage is the same. Current needs to increase if you want to increase the power. If you want to decrease the power, then the current must decrease. So if I increases, what must happen to R? Does it increase or decrease? Has to decrease, of course. V equals IR. And if I decreases, then R increases. So as a customer comes back and says, I want this for low power, high power applications. No, low power application. Nothing is mentioned about voltage. You assume voltage is going to be the same. For low power application, that means current needs to be reduced. If current needs to be reduced, then you increase the value of resistors R. And your calculation, let's say it comes out to be a total Thevenin equivalent of 25 kilo ohms. These are linear circuits comprised of linear resistors, meaning voltage and current have a linear relationship. V equals IR. So V is proportional to I. It's a linear circuit. If you scale R and you keep the other one constant, then the other quantity changes with respect to R, right? So you change RTH. Let's say you wanted 25 kilo ohms. All you have to do is scale up or down the resistance values. So if RTH is going from 5 to 25, it's a factor of 5. You simply multiply all resistors by 5. And so we can, instead of 10K, we are now using 50K. So it'd be two 50K resistors in parallel in that circuit. If this was a high power application, that means the current needs to increase. If current needs to increase, that means we decrease the resistance. And so let's say if you want an RTH of 1 kilo ohm instead of 5 kilo ohms, well, now we start with 2K and 2K in parallel. Okay, that's the change we would make. And this works because it's a resistive circuit, it's linear, and it's a linear resistive circuit. Okay. Does that make sense? Right. So we did one topic in the previous section, and then we stopped here. So that's what I'm going to do. Um, okay. You're all familiar with resistance R. Right? Resistance is R. Unit is ohms. It's the only unit that uses, well, at least the only unit, only the most common unit that uses a Greek letter as its symbol. So it's uppercase omega. Note the unit's ohms. Mathematically, it can be given by rho L or A. This rho is the Greek letter rho. It stands for resistivity. Resistivity is a material property of a material. And you can use the resistivity to design resistors of different value. This is the area, cross-sectional area A of a piece of material. And then the total length of that material. Okay, so if you have any piece of material made out of any material, then it has its own resistivity, and the length and the cross-sectional area gives us the resistance of that material. Okay. The reason we're talking about this is to introduce something known as conductance. Conductance is the reciprocal of resistance R. Okay, it is noted with the letter G. It has the unit Siemens. It is named after the Austrian-German physicist Siemens. Noted with uppercase S. Often it's also known as mho, M-H-O. Mho. A practical look at this is in long distance transmission lines. Okay. We talk about circuits as ideal conductors, right? On paper, when you're performing analysis, we're talking about wires. Wires, very low resistance, 0.2, 0.3 ohms, definitely less than 1 ohm. But this is where it comes from, rho L or A. You can take the best conductor on the planet, which has a few milliohms as resistance. But think about long distance transmission line that go over hundreds of miles. Now the length of each conductor is hundreds of miles. And so it has some resistance. When it has some resistance, you're going to have opposition to the flow of current. That means a lot of energy is wasted during transport. Okay, it's a lot of energy that is wasted during transport. And the power equation states that the power either that is lost or transmitted is square of the current. So P is equal to I square times R. So not only is your resistance large, but if you send huge amounts of power by increasing the current, then the losses are going to increase corresponding to the square of that current. Okay. So while North America uses 120 volts, most of the world uses 240 volts. This is the reason why. Instead of increasing the current, you increase the voltage and you send it over long distances, you minimize your losses during transmission. Okay. Coming back to our point, why are we talking about conductance? Well, when we look at parallel circuits like these, in parallel circuits, oftentimes we are dealing, not oftentimes, if you're trying to work with currents and current division, we need to find REQ. REQ of parallel networks is the reciprocal of the sum of the reciprocals, right? 1 over R1 plus 1 over R2, right? If it's 2 resistors, it's simple. If it's 3, it's still simple. But if it's 4, 5, 6, or tens of hundreds of resistors in parallel, then it gets very unwieldy, trying to find, that REQ and those current division and everything. And so that time, it is useful for us to actually write our equation in conductances. Current division principle applies only to resistors in parallel. It's determined by finding total voltage V in that parallel sum by finding REQ. And REQ, of course, is R1 over R1, R2 over R1 plus R2. I1 is V over R1. I2 is V over R2. Hence, I1 is, and V in this case can be given by R1, R2, or R1 plus R2 times I times 1 over R1. Okay. So it becomes rather unwieldy trying to do these calculations. So we can use conductances, and in conductances, we can write I1 is simply G1 or G1 plus G2 and times I, of course. Far simpler. You simply find the reciprocal of each resistance. So that gives you conductance of each resistor. And from that conductance, you simply G1 over G1 plus G2. If you have 3 resistors, it's G1 over G1 plus G2 plus G3. 4 resistors, G1 plus G2 plus G3 plus G4. So it'll be similar to voltage division. Very similar to voltage division. Okay. All right, let's take a pause. Let me know if you have any questions. Yes. The last statement, the last equation. I mean, how did we obtain G1? This one or this one? This one is simply, so voltage across that parallel combination is I times REQ. REQ for those 2 parallel networks is R1 times R2 or R1 plus R2. So we simply plugged REQ in that equation and we found V, which is this V over here. So V over R1, this right here is V. Okay, that is V, and V divided by R1. That's what that equation is. Does that make sense now? Okay, that's all it is. And then 1 over R1 is G1. So G1 goes in the numerator. And then the reciprocal 1 over R1 plus 1 over R1. So this G1 in the bottom here is 1 over R1 plus 1 over R2. If you take the reciprocal of this, 1 over G1 plus 1 over G2 becomes 1 over R1 plus 1 over R2 in the reciprocal. And this is REQ. right? REQ of two parallel resistors. And so if it's REQ of two parallel resistors, it's G1 plus G2, or 1 over G1 plus G2. That's where the equation comes from. Okay. Make sense, right? It's a lot of info. The slides go like, these 4 slides or 5 slides, but there's a lot of small concepts and a lot of things go in there. So I always recommend to students, if you have time after class, just spend like 5 or 10 minutes, not more than that. Just 5 or 10 minutes, just so that you retain a little bit of things, and then take a break. And then maybe later today or later tomorrow, that's when you go back and refresh and review the slides. Okay. 30 minutes or more is the maximum for learning. 50 minutes lecture is pushing it. There's a lot of information in there. So again, just review for like 5-10 minutes and then take an in-depth review after taking a break. But definitely review for sure. Okay, there's a lot of things in there, lots of tiny things. All right. Okay, we'll end class here today, and we'll pick up here again on Friday.